The Waikato River Bridge, completed in May 2022, is a key addition to Hamilton's infrastructure, connecting the growing suburb of Peacock with Hillcrest and the eastern parts of the city. This four-lane bridge, including dedicated bus lanes, spans a total of 180 meters, with 96 meters stretching directly across the Waikato River. Notably, the bridge design prioritizes ecological sensitivity, especially regarding the impact on native wildlife and the surrounding environment. A single Y-shaped pillar on the south bank supports the bridge without requiring piers in the river, minimizing disruption to the habitat of local species, including the native long-tailed bats. During construction, two massive steel structures, each weighing over 200 tons, were carefully installed using one of the largest crawler cranes in the country, showcasing the project's engineering prowess. Beyond functionality, the bridge underscores Hamilton's commitment to sustainable urban expansion. Its integration within the surrounding transport network enhances accessibility for vehicles, public transit, and pedestrians, supporting a vision for a connected, sustainable, and eco-conscious community in Peacock. The Waikato River Bridge stands not only as a modern engineering achievement, but also as a model for development that respects and preserves the natural landscape it inhabits. The installation of the Shinri Church Puss Girder Crane is a significant engineering project, designed to enhance operational efficiency and support large-scale construction or maintenance tasks at the church site. Girder cranes are crucial for heavy lifting, often used in various industrial and construction settings, and their installation requires a high level of expertise in structural engineering, logistics, and safety management. The Shinri Church Puss Girder Crane is designed to handle substantial loads and facilitate the movement of materials over long distances. Its structure typically comprises a main horizontal girder supported by robust beams and trusses, which allow it to handle heavy loads safely. During the installation process, the initial steps involve careful site assessment, including measurements, load analysis, and structural evaluations to ensure the crane will be able to function optimally and safely within the constraints of the church's location. Following this, teams begin the assembly, starting with the base supports and gradually adding sections of the girder while checking for alignment and stability. Each part of the girder crane must be securely connected, tested, and adjusted as necessary to ensure that it can handle dynamic and static loads effectively. Given that safety is paramount, the installation team strictly adheres to guidelines and regulatory standards, using harnesses, stabilizers, and other protective equipment to prevent accidents. The Ochoko Creek Bridge in Prineville, Oregon, is a critical infrastructure component along Oregon Route 380, linking key community areas, including a hospital, schools, and recreational sites. Originally constructed in the 1920s, the old bridge was no longer capable of handling the increased traffic loads it was expected to support. Due to structural limitations, a replacement became essential to ensure safety and maintain effective transportation across Ochoko Creek. To address this need, an innovative approach called Accelerated Bridge Construction, ABC, was implemented, minimizing closure time and disruption. The ABC method involves a unique technique where the bridge is constructed off-site and then slid into place, saving considerable time compared to traditional bridge replacement methods. Using this approach, the road closure period was reduced to only 3 weeks, whereas a conventional process would have taken over 3 months. Initially, the older bridge structure was demolished, beginning with the bridge deck, the surface where vehicles travel, and continuing down to the girders, which provide the structural strength. These materials were dismantled and removed from the creek area using excavators and heavy machinery, clearing space for the new, stronger bridge. Once the old bridge was removed, the creek bed was prepared to accommodate a wider bridge design. Large boulders, referred to as riprap, were placed along the creek's banks to stabilize the area, and gravel was added for further reinforcement. To support the new bridge, 70-foot steel piles were driven into the ground, creating a solid foundation. A concrete pile cap was then installed, connecting these piles to provide a unified base for the bridge structure. The bridge slide itself was a complex task, requiring precise coordination and powerful equipment. Two 100-ton hydraulic jacks were used to incrementally push the bridge into position. These jacks, mounted on either side of the bridge, were operated in stages, advancing the bridge by about a foot at a time. To facilitate the slide, the bridge was placed on Teflon pads, allowing it to glide smoothly over stainless steel plates that minimized friction. The final stages of the construction involved laying asphalt to connect the bridge with the roadway, completing a safer, more reliable bridge for the Prineville community. This modernized Ochoco Creek Bridge now offers a durable link across Ochoco Creek, supporting local transportation needs and ensuring continued access to essential services. The installation of the Sioye Bridge, a continuous bridge spanning 50 meters, marks a significant engineering achievement in the construction of Expressway No. 30, connecting Songju to Yeongdeok, South Korea. This bridge, classified as a PSC, pre-stressed concrete east beam bridge, was constructed as part of Section 3 of the larger Expressway project, which aims to improve regional connectivity and support increased transportation efficiency across the area. The video documentation of the bridge's construction and installation on July 21, 2014, highlights the careful planning, execution, and technical precision involved in the project. Led by Sungmin Kwok, the Sioye Bridge project forms part of a broader highway initiative, Expressway No. 30, which is a key infrastructure project linking the cities of Songju and Yeongdeok. This expressway will reduce travel time, enhance safety, and support regional economic growth by improving logistics capabilities. Section 3 of this expressway, where the Sioye Bridge is located, includes a critical crossing point that requires reliable, long-lasting infrastructure. To meet these needs, the project team chose a PSC East Beam continuous bridge design, a technology known for its durability, structural strength, and ability to efficiently handle high traffic volumes. The bridge was engineered with a span configuration that optimizes load distribution while balancing aesthetic and functional requirements. The Sioye Bridge spans a total length of 280 meters, with a unique span configuration of 40 plus 50 plus 50 plus 50 plus 50 plus 40. This layout was chosen to meet both structural stability and aesthetic considerations, ensuring the bridge could support heavy loads without compromising on visual appeal. Each of the main spans, measuring 50 meters, is part of the PSC E-beam design, known for its ability to withstand significant stress while minimizing material usage. With a width of 24.3 meters, the bridge comfortably accommodates multiple lanes of traffic, reducing bottlenecks and allowing smoother flow, even during peak hours. The height of the bridge stands at 2.7 meters, an optimal measurement that balances necessary clearance with the structural stability required for a bridge of this length. The PSC E-beam technology used in the bridge incorporates pre-stressed concrete, which is manufactured by embedding steel tendons within the concrete to create compressive stress. This technique not only enhances the strength of the beams, but also increases their durability, making the bridge more resistant to environmental factors and structural wear over time. The installation process for the Sioye Bridge required meticulous planning and coordination. Since the PSC E-beam construction involves producing pre-stressed beams off-site, they were carefully manufactured to specifications before being transported to the construction location. This approach allowed for precise quality control and reduced the risk of weather-related delays, a common challenge in on-site concrete pouring and curing. Once on-site, the beams were installed using specialized cranes and equipment that enabled the team to lift and secure each beam into place with minimal disruption to surrounding activities. The E-beam construction method's adaptability helped streamline the process, allowing for faster installation compared to traditional on-site methods. Under the leadership of project manager Sungmin Kwok, the installation of the Sioye Bridge demonstrates the potential of PSC E-beam technology to enhance infrastructure development in South Korea. Kwok's guidance ensured that each stage of construction adhered to strict safety and quality standards, underscoring the importance of professional expertise in executing complex engineering projects. The installation of PUS girders on the Wongdeok pedestrian bridge is a complex and impressive engineering project, requiring precise planning, specialized equipment, and skilled operators. A PUS pre-stressed ultra-slim girder is a high-performance beam that supports bridge structures with enhanced strength and reduced weight. For the Wongduk pedestrian bridge, these girders were selected due to their durability, resistance to harsh marine conditions, and the ability to span long distances without excessive bulk. The installation process involves positioning the PUS girders over the sea, requiring the use of a 600-ton floating crane. This heavy-duty crane is essential due to the substantial weight of each girder and the challenges of working over water. A floating crane, as opposed to a land-based one, provides flexibility in maneuvering and positioning the girders precisely where they are needed. This setup also reduces the need for temporary land structures or extensive staging, which would otherwise complicate construction and increase environmental impact. The installation begins with transporting the PUS girders to the site where they are lifted by the floating crane. Due to the sheer weight and size of these girders, careful calculations are conducted to ensure the crane's stability and lifting capacity. Weather and sea conditions are also closely monitored, as any fluctuations in wind or tide could impact the crane's ability to safely place the girder. With a lifting capacity of 600 tons, the crane can handle these large girders, but operations are halted in high winds or rough waters to prioritize safety. Once the girder is lifted, it is carefully positioned and aligned with the bridge's existing supports. Workers on site communicate closely with the crane operator to ensure precision, as even slight misalignments could lead to structural issues. Once in place, the girders are securely fastened, and quality checks are performed to verify stability and alignment. The use of PUS girders and a 600-ton floating crane streamlines the installation process, enabling rapid and reliable construction over challenging marine environments. The construction of the new Lyminster Bridge in West Sussex represents a transformative infrastructure project designed to improve connectivity, safety, and traffic flow in the region. Situated near Wick, the bridge is part of a broader effort to ease congestion on the A284, which serves as a crucial route for residents, businesses, and visitors traveling between the towns of Littlehampton and Arundel. The project has been captured in a comprehensive 10-month time-lapse video by BCM Construction, offering a fascinating glimpse into the complexities and scale of modern bridge-building efforts. For many years, the A284 road in West Sussex has faced significant challenges, particularly around the level crossing in the village of Wick. This area has been a long-standing bottleneck, causing extensive delays and safety risks for both pedestrians and drivers. With increased demand on local infrastructure, it became essential to develop an alternative solution to ensure safe and efficient travel between Littlehampton and Arundel. The new Lyminster Bridge was conceived as part of the A284 Lyminster Bypass Scheme, an ambitious project by West Sussex County Council to reduce traffic, improve road safety, and create a seamless route for travelers in the region. The Lyminster Bridge specifically aims to bypass the congested level crossing, eliminating frequent delays caused by passing trains. By providing a direct crossing over the nearby River Arun, the bridge will reduce journey times, minimize the risk of accidents, and support the area's growing population. Additionally, the new bridge is designed to integrate with existing roads and infrastructure, ensuring minimal environmental impact while maximizing long-term benefits for the community. The construction of Lyminster Bridge was a multi-phased process that required careful planning and coordination across various stages. Over the course of 10 months, BCM Construction oversaw every aspect of the project, from the initial groundwork to the final touches that transformed the structure into a functional part of the road network. Each phase involved unique challenges and solutions that reflect the complexities of modern infrastructure development. Following the completion of the foundational work, the next major milestone was the installation of the bridge deck, the surface on which vehicles will travel. Large steel beams were lifted into place with cranes, providing structural support for the concrete deck. Once the deck was in position, workers poured concrete and allowed it to set, creating a smooth and durable driving surface. Additional features, including safety barriers, drainage systems, and street lighting, were added to enhance safety and usability. Finally, road markings and signs were put in place, signaling the project's readiness for public use. Bridge construction projects like Lyminster Bridge often face a variety of challenges, from environmental considerations to logistical complexities. This project had to be carried out near active railway lines, which required careful timing and coordination with railway authorities to avoid disruptions. Weather conditions also posed occasional challenges, as heavy rainfall can delay groundwork and concrete curing times. The 24-hour replacement of a transporter bridge is an impressive engineering feat, often undertaken to modernize infrastructure while minimizing disruption to daily life. Transporter bridges, a type of bridge used to transport vehicles and passengers across large waterways, have a unique structure that combines elements of both suspension and ferrying technology. Given their distinct design and limited numbers worldwide, their maintenance and replacement demand a sophisticated, carefully orchestrated approach. The goal of a 24-hour replacement project is to dismantle the existing structure and install a new, state-of-the-art bridge in a single day, reducing prolonged road closures and inconvenience to the local community. This fast-track approach has become increasingly popular as urban areas prioritize efficiency and minimize the impact on local economies. Transporter bridges have been used for over a century, primarily because of their ability to move heavy loads over large spans without needing extensive bridge foundations or disturbing marine traffic below. This type of bridge uses a suspended gondola to carry vehicles and pedestrians across the water, allowing the clearance of high vessels without needing an opening mechanism or traditional supporting structures. Many transporter bridges are considered historical landmarks and are built to last, but as they age, the structural requirements and load-bearing demands on them increase. Moreover, with advances in technology, older bridges may lack the safety and efficiency features of modern ones, necessitating their replacement. Replacing these bridges, especially in urban or densely populated areas, can cause major disruptions. Thus, a rapid 24-hour replacement option offers an attractive solution that minimizes interruptions. To accomplish such a massive project within a day, engineers employ innovative techniques and detailed planning, leveraging prefabrication, specialized machinery, and a highly coordinated workforce. When the day of the replacement arrives, the project team initiates a highly choreographed sequence of operations. First, traffic diversions and safety protocols are put into place to ensure the security of both workers and the public. The dismantling of the old bridge involves cutting through existing joints and securing its parts with heavy-duty cranes. In some cases, explosives may be used for rapid deconstruction, although this depends on the bridge's size and proximity to populated areas. After the old bridge is dismantled, heavy machinery moves the prefabricated sections of the new bridge into place. This process is swift and requires a specialized workforce that can work around the clock to ensure each component is connected precisely. As one section is secured, the next is brought into position, making the replacement process a seamless, non-stop assembly line of operations. Safety is paramount during a 24-hour bridge replacement, with multiple redundancies and protocols in place to protect workers and the surrounding community. Teams often employ drones to monitor the site, providing real-time data that enables swift responses to potential issues. Environmental concerns are also carefully managed. Engineers are attentive to factors such as noise, dust, and the potential impact on local wildlife and ecosystems. Waterway navigation, if relevant, is redirected in advance to prevent interference with maritime traffic. The 24-hour transporter bridge replacement demonstrates the potential of modern engineering to overcome traditional constraints. By completing the project in such a limited time frame, engineers and construction crews reduce prolonged disruptions, benefiting local residents, businesses, and commuters alike.